So basically, yeah. So my name is Ashu, as you have already been introduced. This talk is about how you would scale a single PostgreSQL instance to the limit of a machine. Basically, the whole idea of a database is that you want to be able to use the hardware resources that are present on the machine to the fullest extent. Before I go into how do you do that, the question is, why do you want to do it? While all the talk is about having horizontally scalable systems, having multiple machines to be that you can control inside a cluster, or basically put hundreds of instances of PostgreSQL to serve your application. Why do you want to do it on a single machine? Here is my answer. You want to do it because this makes sense from a cost perspective. This graph represents the cost comparison of multiple machines versus a single machine having the same number of CPU. As you can see, the graph is pretty much linear. Both the graphs pretty much coincide. So the cloud providers have been able to manage to give you the cost advantage in a single machine that you would get on multiple machines. So that cost argument no longer holds, that if you cram up a lot of resources on a single machine, you'll pay more. Now the point is, if I don't have the cost advantage, do I really want to manage the complexity of multiple machines? Because when you have a lot of machines, you have to manage the complexity, you have to pay the tax. Basically the CPU resources, the memory that the operating system is going to take, the I/O that the operating system is going to do, extra monitoring that you are putting on each of those machines, you'll pay that tax anyway. So unless you really need it, unless you are actually going out of the limits of a single machine, I personally think it doesn't make sense, and that graph also tells me that it doesn't make a lot of sense to over-engineer on multiple machines. Let's first hit the limits of a single machine and then do it. So before I actually go and talk about how, just a little bit of introduction why you should listen to me. I've been building databases from scratch for more than 6+ years, and I've been maintaining them at production scale. Started from 0 to tens of petabytes, not on Postgres, but on multiple different databases. Currently, I'm serving as CTO at Clarisights. I'll be introducing Clarisights as part of this presentation also. I am currently an official Apache HBase committer, and in the past, I was doing data infrastructure at Facebook and at Rocket Fuel in California. So before I go into how you scale PostgreSQL, let's first understand how PostgreSQL is being used as Clarisights. For that, we need to understand what Clarisights is about. It's a SaaS platform, real-time interactive contextual reporting. That's the exact sentence I just copied from our website. But what it means is that we are targeting performance marketing teams to derive the maximum value out of their large data sets that they get from marketing reports. It's a single vertical solution to solve 3 problems in a single product. To be able to do API integrations with Facebook, Google, LinkedIn, Snapchat, different advertising data sources, transform that data, enrich that data so that performance marketers can use that data. Because marketers are not engineers, so to expect them to write code to be able to extract value out of the data is not correct. So you need a tool that does data enrichment and transformation on its own. And it gives you interactive analytics. What this means is that you are able to run analytical queries on billions and trillions of rows of data within a few seconds, not in minutes and hours. This is what Clarisights does basically. It takes data from Facebook, Google Analytics, Twitter, and like 30 more different data sources, and it turns into this. You get reports on this data on different dimensions and different metrics. For example, I want to ask a question: what is my spend in a particular city across all of my data sources like Facebook, Google, and like any place where I'm putting my ads on. So this is a common question that I want to ask. I don't want to ask it just specifically for Facebook or Google, right? So this is what Clarisights does exactly. What this leads to is there are interesting data engineering challenges that arise at Clarisights. The data engineering challenges basically include that you have aggregate time series data for each ad or for each keyword, basically any object that you see on the advertising. There are hundreds of dimensions. What I mean by a dimension is, for example, I said city, right? What is my spend in a city? City is a dimension. I want to see how much I spent in Bangalore, all the ads that were targeted to users in Bangalore. So Bangalore becomes the value of the city dimension. So what this means is that there has to be some level of data enrichment that is dependent on the kind of customer. Like some people are interested in the city dimension, but other people might be interested in the type of product. For example, a food delivery company will be interested in whether it's burgers versus pizzas. So these dimensions are created by users after the data is ingested. So that is dynamic. That's very different from what a usual OLAP workload would look like, where you would have all of your data defined before the ingest. You would have a schema in place, you would have the dimensions defined in place. This actually increases the complexity of the problem. Then you have metrics associated with these dimensions. They are also very wide rows, more than 10,000 metrics. These metrics also update. There are historical updates. The data that I ingested 1 month ago, that data will also change. So what we are doing is high dimensional analytics on data that mutates, that changes. What this means is that what we need is an HTAP system, hybrid transactional analytics processing, not just an OLTP, but an OLTP combined with an OLAP system that can handle more than 5 billion updates per day, more than 400 billion reads per day. It should work in a high dimensional space with dynamically defined dimensions. So yeah, basically what we did a lot of research. What are the systems out there that can serve this use case? There are a bunch of HTAP systems out there, distributed HTAP systems that can handle this kind of scale. They don't work in a high dimensional space, and the reverse is also true. The ones that work in a high dimensional space, they are not able to handle the kind of scale that we are throwing at the problem. So it's still an area of research in the industry, and we did not find a single system that solves it. So we started asking this question, why isn't there a single system that actually solves this problem? And this actually goes back to the Rum conjecture. What is Rum conjecture? Rum conjecture is basically a triangle. There are 3 vertices of a triangle: read, update, and memory. What this means is that any system that is out there, what this Rum conjecture basically suggests, any system that is out there, you can try to fully optimize the system on only 2 vertices of this triangle, not 3. You can either optimize for point reads, which means you can put a B tree structure, which is Postgres. You can optimize for writes, something like an LSM tree, HBase, Cassandra. You can optimize for memory. But I think we all agree here that everyone would like to optimize for memory. Nobody wants paying extra dollars or extra rupees. Usually, in my experience, what I've seen is that the memory is the fixed vertex. You are always trying to optimize for memory to the extent that you can, but then you try to compromise your access patterns in a way, whether it scales well for reads versus writes, or you find an adaptive solution to the problem, which is where the middle of the triangle is. You find a balance between writes and reads. I'll explain that in more detail later when I explain the access patterns. So how did we get around Rum conjecture? We basically, instead of introducing one system, we introduced 2 systems in the mix. Something's wrong with the slide. It's supposed to, okay, I don't know what happened. There was a diagram here which basically tells that there are 2 systems. One is OLTP, which is Postgres, where you can do transactions, where you can do basically your writes and updates. But it is not optimized for writes. That is the problem. So you modify your access patterns in a way that you can do writes and updates, and you are optimized for reads so that you can read from the system and write to an OLAP system periodically. So you have 2 systems in place. One is OLTP, one is OLAP. You do a periodic sync between these 2. Your OLTP system becomes source of truth, and your OLAP system becomes the analytics system, where you will where your customers will throw the analytical queries. So now I'll talk about scaling. How did we scale PostgreSQL with this kind of workload where we are using it as an OLTP system, but we have to do a periodic sync to the OLAP system also. But before I go into the specific approaches, we had a bunch of general approaches in mind that we'll basically go about doing them. We could adopt two approaches. Try to scale PostgreSQL as a service. Basically, either do system tuning or do config tuning on Postgres, put better hardware, something to do which the users of PostgreSQL don't control. The other way of doing it, you actually introduce RAM-aware access patterns. So you modify your workload in a way that it is more conducive to the adaptive pattern for the read, update, memory conjecture. So the very first thing that we thought about, okay, let's try to optimize for throughput. Why? First of all, in Postgres, you cannot really optimize for write latency, because PostgreSQL write model is asynchronous. That might sound like a surprise to a lot of people, because we do writes, we get an acknowledgement, it's consistent, Postgres tells you that it's there, you believe it, right? That's what it is, but under the hood, it is actually backed by an asynchronous write system. I'll explain that also, how that is, but the whole idea is that Postgres is meant for higher write throughput, but not better write latency. The reverse is true for reads though. Postgres is very good at giving you both better read throughput and better read latency because of the B tree structure that it holds. But luckily our use case was throughput driven. We are not latency bound because Postgres is just our ingestion source. It's not the OLAP system which the customers are directly talking to. So Postgres is not really latency sensitive in our use case. So how do you optimize for throughput? Naive approach. We want to do more writes, let's throw more writes at the system. Concurrency. Since latency is not a problem, we throw a massive number of clients at Postgres. More than 10,000 plus connections at a single point of time to a single machine. What is the problem? Every connection has its own memory overhead, and Postgres has a memory limit of a single slab of memory allocation of 1 gigabyte. This is hard coded inside the code. It's not a config that you can tune. If you try to allocate one single chunk of memory more than 1 gigabyte, you will face an error. Basically, you don't do it explicitly, but there are ways that you can force Postgres to do it, and then it will throw an error. One way is you throw more connections. For us, it turned out to be somewhere close to 10,000 connections. After that, our queries to the catalog tables started failing because it could not allocate enough memory. So yeah, that is not really the solution. We want to do more than 10,000. We want to throw more concurrency at it. So how do we do it? One general approach that people use is they put a proxy. They put a connection pooler on top of Postgres. So PG Bouncer is pretty much the standard right now. If you just want to do connection pooling on Postgres, it supports 3 different pooling modes: session pooling, transaction pooling, statement pooling. Basically, what transaction pooling is that it will try to maintain the same connection for the same transaction, but across transactions you don't get that guarantee. Similarly for statement and session. Is the graph visible to you guys? No? Okay. All right. But the numbers are right. Okay. Something happened with the slides during the transformation. I don't know why it's not visible. But the idea is that when we started using transaction pooling mode of PG Bouncer, we were able to reduce the number of connections that we are throwing at Postgres while keeping the same number of client connections. So this is just a snapshot. We do hit more than 10,000. In this snapshot, we were actually hitting 6,600 client connections. For that, we are only having 164 server connections to Postgres. That obviously it doesn't work every time. It depends on how your workload is. If you have very short running transactions, you will actually have this kind of workload. But then the argument is, should you really have long running transactions? You shouldn't. That has other problems that I'll also explain later. But it's not a win-win situation. We do lose something by using transaction pooling in PG Bouncer. We lose all the session specific features basically. Anything that works in a single session in Postgres That is what we lose. So prepared statements are not available. Cursors with hold, not available. Advisory logs, they are used by Rails migrations. The reason I mention Rails is because we use Rails in our backend app. We lose all of those capabilities, but that was an explicit choice we made to be able to drive more throughput through Postgres. We will lose all of these session specific features. They are not very important for us. For example, prepared statements. We did an analysis, we did a benchmark. We found that our queries, since they are not latency sensitive, they are really long running queries, something that takes around 30 seconds to run. Their prepared statements don't really help well because the planning time, the query planning time is very small compared to 30 seconds. So now that we have tried the naive approach, just throwing more workload, throwing more concurrent workload at the problem, now we are one level deeper. Let's try to optimize specific access patterns. Reads, writes, let's try to see what is going on there. So first point of attack was scaling reads. So remember I was talking about that OLAP sync where you write to Postgres, then sync to your OLAP system periodically. Loading properly on the laptop that we have. So I think we'll just make do without the graphs and the figures. Yeah. The point is that we are trying to do the OLAP sync, and if you remember, as I was explaining that periodically we sync from the PostgreSQL to our OLAP database. What these queries look like, we query over several days worth of data. It goes over a few billion rows. The queries look like this. You don't need to read the whole queries, but the idea is that there is a sum, which means there is an aggregation function that is involved on doing group by on a bunch of fields. So it's not a query that's just doing filtering. You have to do a group by, and then there is an aggregation function that is involved. Since we are doing OLAP sync, it's not just a simple copy. It has to do some level of transformation on the data that it has read from Postgres. So what we tried was, the initial approach was, we'll just use something called find in batches that is there in Rails. You don't need to know how it works, but the idea is that it changes the query that is being thrown to Postgres in a very specific way. It adds an order by on the primary key, adds an offset of, basically if you are trying to iterate in a batch of 1000, it will add offset 1000, limit 1000, offset 2000, limit 1000, offset 3000, limit 1000. That is how it will iterate. And it has to add an order by primarily because if there are writes while you are doing this, you don't want to miss the new records. If you are actually not sorting on primary key and there were writes that came in between, you might actually miss some of the records. So as you can see, this will not work. There is a lot of redundant work here. The same query is being thrown multiple times. The filter is supported by the index, but still the filter is happening every time. The bigger problem is you have to do a group by. Only then you will do the offset and limit, right? So there is multiple times you are doing the same work again and again. So immediately we thought, okay, we'll try to remove the redundant work. We will use cursors in Postgres. Problem with cursors, open a transaction. This is a query that takes long. We are doing transformation of a lot of data. It will take even 30 minutes to an hour to do that. We don't want to have transactions open for that long. So the second optimization that we did, okay, let's not use transactions. Let's use cursors that persist outside of the transaction. Cursors with hold. Now, the problem with that is it works well, but not in our setup. We have already made the choice to forego all the session specific features. Cursors with hold don't work with transaction pooling. We again basically went over our approach. Okay, can we get rid of transaction pooling, come back to session pooling? But based on benchmarks and how much code changes that we'll have to do just to support this specific feature, they were a lot. So we decided to figure out a different approach. The third approach that we thought about was, okay, let's use materialized views in Postgres. The query that we are running, we can just materialize to a view, right? The problem with that is you have to still refresh it periodically. It doesn't get rid of older data. So you have to get rid of the older data somehow anyway. So still not strictly better than just writing to a table. Then why not write to a table? So we thought, okay, we'll use temporary tables in Postgres and What this means is that the result of the query, write to a temporary table, do whatever you want to do on this table. Here you don't need you don't need the order by, you don't need the group by, because the result of the order by and group by has already been written in that format to the temporary table. So all you need to do is iterate over the records in the table. So we got it right? Seems like it. We pushed to staging, tested it, it worked well. Pushed to production, we were happy, but we didn't get it right. As soon as we pushed to production, this is what happened. Our replication stopped working. And the reason it stopped working is temporary tables are still written to the Readahead log. Why? Why would you write temporary tables to the Readahead log? I don't know why Postgres chose to make this decision, but the point is, sorry. So that is, okay. I might be wrong, but this is something that I have tested at least with Postgres version 10. Yeah. So that is why that is the next slide basically. So temporary tables are still written to Readahead log, which means that even though you are going to delete that table, there is still a lot of writes you are doing to the Readahead log. You're still doing a lot of replication, and I'm talking about replication here because that is the only thing that broke. But a lot of things got impacted. You are still doing a lot of writes to whatever. If you have your workload on the same disk, you're impacting your disk. If your Readahead log is still in the same directory, so you're still doing a lot of writes to that. So replication broke. It couldn't run fast enough to keep up. So the final solution that we implemented, instead of using temporary tables, we will use normal PostgreSQL tables because they do support unlogged. They give you the ability to not write to Readahead log. We only need it for a small period of time. Why do we want to log it? Even if we lose this data, we are anyway the job is going to fail, so we are anyway going to run it again. So it's an idempotent operation. We use unlocked tables, no writes to Readahead log. Replication doesn't need to stream anything, doesn't need to recreate anything. But one thing that you still have to be aware of, it's still a write to the disk. So it's a good idea to separate out these temporary workloads that you put on a separate disk. I'll discuss that later in more detail in terms of how you want to segregate your traffic. But in this case, we ended up doing that. But we still lose something. Because we are using normal tables, now we have to delete those tables. It's not as bad as deleting individual records from the table from a materialized view, or basically something that has all the data, but still you need to have a delete table. It sounds like a very innocent operation, just do a delete table, right? But the problem that happens is that you start seeing fragmentation in PG class. PG class basically holds reference to all the objects that are there in Postgres. If it starts seeing fragmentation, your whole Postgres slowly becomes slow. This is something that we recently noticed about a month ago. So we still need to find the solution to that. It's not as bad because the fragmentation grows slowly, but this is something that to be aware of. If you are doing a lot of these operations, create table, delete table, create table, delete table, you will basically face the same problem. Now, one level deeper, we tried scaling the biggest workload for reads, but now let's look at individual queries, specific queries that we are doing, and try to fix them. The point is that we want to attack the impactful queries, not just slow queries. So our first attempt that was working on the assumption that we just need to put indexes, or we just need to attack or optimize the queries that are slow based on the suggestions that are given by tools like PG Hero, by Dexter. They work out well on a specific axis, but there is still another axis. You still need to attack queries that are impactful. What does that mean? It means that it's possible you are doing queries which are not slow enough to be caught by these tools, but you're just doing them so many times in your day. So you still want to be able to optimize them. You still want a view, something that tells you that, okay, these are the queries that are impacting your system. Whether you can optimize it or not, it's up to you. That's a capability question, but you still need that axis. You still need that view where you can look at it. So the second approach was, okay, let's try to look at it from the application perspective. If we try a sampling profiler from the application and try to profile the calls to PG from the application side, we will be able to, since it's a sampling profiler, it's not a duration-based profiler, not a latency-based profiler, you will be able to see the queries that are being triggered the maximum number of times, and you will be able to see the queries that are happening for the longest time. So you get both of them. But the problem with this is doing it on the application side ties it to a specific piece of code. If later we have a different workload that is running in some different language like Golang or Java, you'll have to implement it there. So why not try the same problem on the same solution on Postgres side? Have a sampling profiler on PGStat activity. This table basically stores everything that is happening right now. All the queries that are executing, well, executing is the wrong word, but anything that is active, idle, that the Postgres is working on right now, that is being shown in the PGStat activity. The problem with that is it doesn't show you the duration, but it does show you all the individual queries, even the parameters of them, as opposed to what the PG statement activity, PGStat statements shows you. So again, the diagram is missing. The point is that we are going to do, we basically take the snapshot of PGStat activity every 10 seconds or every 15 seconds and ship it to an external system, Elasticsearch, your choice, something that allows you to do a group on the query IDs. We introduce a unique query ID. It's very easy to do from the application side. Even if you don't do that, you can still do a hash of the query before you ship it to your external system. So what this allows you to do is you will basically be able to see something like this. Good that we have this picture. It's not a graph. Okay. So as you can see, what we have on the y-axis is the count of how many times a particular query on the x-axis was seen. So it's just a count in a particular duration. It's possible the same query was fired 10 times, 100 times, or it's possible the same query was running for all of these 100 seconds or 1000 seconds. So that lets you basically mix your intent. It tells you the exact intent that I want to just look at the impactful queries, not just the slow queries. Now that we are done with scaling reads, now let's attack the other access pattern, scaling writes. As I pointed out earlier, PostgreSQL is not write optimized. It's not an LSM system. It's not a differential data structure. It's backed by a B tree. Plus, all the write operations that you do in PostgreSQL. So PostgreSQL basically deals in pages. So whatever write you do, it will be a write to a page that will need to be flushed at a later point of time to the disk again. That's what Postgres calls dirty pages. So whenever you write even a single column in a single row, it will have to pull out that page. It doesn't modify in place, writes a new version of that row. At a later point of time, a separate writer process will come in and see that, oh, this page is dirty, it will flush to the disk. What this means is that even if I'm doing 1 byte, 10 bytes, 1 kilobyte of write, it will still flush the whole page, which is 8 kilobytes. No diagram, I'm just going to skip over it. The point is that the flush to the backend, to the disk happens in an asynchronous thread. So there is a delay that is introduced. That's what we call group commits or group writes in the field of databases. The idea is that we should be able to make use of it to optimize for throughput. The way we do it is, I have borrowed this term traffic shaping from the field of networking, but it applies equally well here. What we can do is that since Postgres is doing a delayed flush, we can change our application or we can change our write patterns in a way that is conducive to that flush, to that commit that is happening. The page that is written, so basically the group of rows that are being written, we can give Postgres the capability or at least throw the workload in such a way that most of the dirty writes that happen, they happen at the same time. So you write only one single page at a time or do a smaller number of writes. So to be able to do that is you group writes on the application side, write to the same table or the partition in bulk. So you have to introduce some level of buffering on the application side, maybe a Kafka stream, or it depends how your write workload is structured. But if you do group writes, you will see better throughput from Postgres. What we saw in production was more than 400% gain just by introducing bulk writes. And believe me, this number is small. Yeah. Mm-hmm. So the workload, the customer of Postgres basically, it is trying to do point writes, write a single row. What we can do is we can introduce a layer in between that tries to group writes to the same partition of a Postgres table or to the same table, which increases the probability of those writes that are coming at the same time to Postgres to fall in the same page of Postgres. Does that answer your question? Okay, yeah, we'll catch up after it, after the talk. But the idea is that you want to reduce the number of writes of pages, not the number of writes to the disk, if you want to optimize for IOPS. Other approach that we tried was traffic segregation. The idea is that we want to reduce the number of IO waits that we do for every unit of data that we are writing, like every kilobyte, every megabyte of data that we are writing to disk. IO schedulers in Linux, they are very intelligent. They try to group writes or reads to the same location on the disk. Disk location is basically a block on the disk. So they merge IO accesses to the same location. So what we do is that segregate different kinds of access patterns. If you understand your application correctly, you can segregate them on different disks. One disk for mixed workload, one disk for very specific kind of workload. Basically, if they are logically different workloads, try to put them on different disks so that Linux also makes use of this knowledge. What we saw from this is we were able to optimize the number of the IO weight, the write IO weight that we were getting on each of the disks by telling Linux that, okay, this workload is supposed to be grouped together. So as you can see, the numbers for write IO weight per average write IO weight for average write rate in terms of kilobytes per second, that number is half for the disk that has similar workload, which has similar tables, where the chances of accessing the same location are higher compared to a mixed workload, where the chances of accessing the same location on disk are lower. So I'm just going to skip over it since we have only 5 minutes. Scaling backups, we can catch up afterwards. For scaling ops, one thing to be really aware of is that Postgres still has this 1 GB memory limit, single block allocation, single chunk of memory allocation limit. So the way auto vacuum works is it will basically go through your do an index scan, right? Try to look for the dead tuples that are there. The problem with that is if the number of dead tuples, if you do a lot of deletes, this size can actually grow over 1 gigabytes. Postgres will stop there. It will clean them and then do a full index scan again. So this becomes a cliff. The 1 gigabyte limit becomes a cliff. So something to be aware of that if you have a lot of updates, if you have a lot of deletes to your tables, you may end up into auto vacuum falling off a cliff in terms of performance. We did aggressive auto vacuuming, changed the number, basically tuned out auto vacuuming configs, but we still have this problem. I'll explain how to mitigate this problem. For indexing, again, if you have a lot of records in your table, any create index operation will take longer, right? So it will it will basically conflict with your transactions that are running. It will conflict with other operations that you are running. It will still affect your production workload. So what we did, basically, Postgres provides concurrent indexing, right? Solves most of the problems. Got rid of long running transactions from the application side, but still affects the production workload. So there is one single solution to both of these problems, and that is partitioning. If you partition your tables, you have a smaller working set for all your operational maintenance tasks that happen on Postgres. So if you basically one index is smaller, so you're creating indexes in smaller chunks, you are auto vacuuming in smaller chunks, you are less likely to hit the 1 GB allocation limit in Postgres. There are a bunch of other knobs to turn. Again, I'll also just skip over. This is something to be aware of. You need to tune the sequential page cost versus random page cost in Postgres if you are using hard drives versus SSDs. SSDs have vastly different cost of accessing a random location compared to sequential workload, HDDs, but SSDs don't. So be aware of your block device. Again, Readahead is something that you should try to understand and tune. XFS is the recommended file system. I would have gone into a little more detail if I had time. But the idea is that you still want to tune your file system, the kind of file system and the file system options that you are putting underneath your PostgreSQL instance. Basically, for every access, every read, even for every read to any file, Linux has to do one more metadata operation, update its last access time. You don't need that for every file in PostgreSQL. Just configure your file system to not store the access time. And last but not the least, understand that you are using Postgres. It's a row-oriented database. It's not a column-oriented database. If you try to read a single field, it is still going to read the row. It's still going to read the page. So there is a high read amplification. If you are cramming up all of your data into a smaller number of tables, if you have logically different data, they should be in logically different tables or different table spaces. So pay attention to the design, the data layout that you are actually putting on Postgres. Again, any questions? Time for only one question, right? No? Okay, we'll take it afterwards. We are hiring, so yeah. We'll do that.